Today, on Guess What I Found Out, we need to recalibrate your sense of scale. Because the star you grew up thinking was impressively large is, cosmically speaking, painfully average. And the stars that actually deserve adjectives are so big that the words we have for big don't really cover it. Let's start with the Sun, because it's the reference point for everything that follows. The radius is about 700,000 kilometers. If it were a soccer ball, Earth would be a 2-millimeter peppercorn sitting about 26 meters away. It contains 743 times the combined mass of every planet in the solar system. By any reasonable human standard, the Sun is enormous. By stellar standards, it is completely unremarkable. Nearby Alpha Centauri is roughly the same size. Sirius A is about twice as large. The Sun sits comfortably in the middle of the main sequence, which is the astronomical term for normal functioning star. And that's exactly what it is. Stars spend most of their lives on the main sequence, a stable phase where the outward pressure of nuclear fusion in the core exactly balances the inward pull of gravity. Astronomers mapped this out in the early 20th century using what's now called the Hertzsprung-Russell diagram, which plots stars by temperature against luminosity and reveals that most of them fall along a diagonal band. That band is the main sequence. The Sun is on it. Most stars you can see with the naked eye are on it. Mass determines where on that band a star sits. More massive stars, well, they burn hotter, shine brighter, and fuse their fuel much faster. Bellatrix, the bright shoulder star in Orion, runs at about 22,000 Kelvin, contains 8.6 solar masses, and has swollen to 200 times the Sun's volume as a result of that intense core pressure. The trade-off, of course, is lifespan. The Sun will last about 10 billion years in total. Bellatrix gets roughly 25 million, with around 7 million left. Massive stars are, you could say, the celebrities of the stellar world, spectacular, profligate, and gone embarrassingly fast. Above about 150 solar masses, stars become so luminous that their own radiation pressure tears them apart. So the main sequence has a ceiling, which means if you want something bigger, you need a workaround. If this is already doing things to your sense of your own cosmic significance, now is a good time to like this video. It gets worse from here. So, the workaround is mergers. When two massive stars collide and combine, they can bypass the usual mass limit entirely. The result, in some extreme cases, is something like R136A1, a Wolf-Rayet star in the Large Magellanic Cloud containing 265 solar masses and a radius about 40 times that of our Sun. Wolf-Rayet stars are what happens when a massive star becomes so energetically unstable that it starts violently shedding its own outer layers, ejecting plasma at 3,000 kilometers per second. R136A1 produces in 4 seconds what the Sun produces in an entire year. There are roughly 220 confirmed Wolf-Rayet stars in the Milky Way. But, you know, they are not long for this universe. But here's where things get spatially interesting. The most massive stars are not actually the largest stars, because once a star exhausts the hydrogen in its core, something rather dramatic happens to its structure. The core collapses inward and heats up. That heat, in turn, ignites hydrogen fusion in the shells surrounding the core, and the energy released pushes the outer layers of the star outward, dramatically and continuously. The star expands into a red giant. For stars in roughly the Sun's mass range, this is, well, the final act before death. The Sun will eventually swell to about 300 million kilometers in diameter, consuming Mercury and Venus, and possibly Earth, depending on who you ask and how optimistic they're feeling. So, if you enjoy learning things that make you feel both tiny and, well, weirdly grateful to be alive right now, why not follow Guess What I Found Out? Stars heavier than about 8 solar masses. You know, they actually skip the red giant phase and go straight to red supergiant. It's the same process, just dramatically scaled up. Betelgeuse, which is the right shoulder of Orion that you can spot glowing reddish-orange on a clear night, has a diameter of roughly 1.2 billion kilometers. If you replace the Sun with Betelgeuse, it would swallow Mercury, Venus, Earth, Mars, and extend well past Jupiter. It's also pulsating, with its edges blurred by enormous ejections of material into the surrounding space, which honestly makes measuring it precisely an ongoing argument among astronomers. Which brings us to the current record holder for largest known star by radius. Scuti in the constellation Scutum, sitting somewhere between 5,000 and 10,000 light-years away. Its radius is approximately 1,700 solar radii. If you put Scuti where the Sun is, its surface would extend past the orbit of Saturn. You could fit roughly 5 billion suns inside its volume. Its surface temperature is only about 40% of the Sun's, which is why it glows deep red rather than yellow-white. It is, by the measure that matters for sheer spatial presence, the biggest thing we've found. Scuti is nearing the end of its life. It's likely transitioning toward a yellow hypergiant phase, shedding enormous clouds of gas and dust enriched with carbon, nitrogen and oxygen, seeding the surrounding region with the raw materials for future stars and planets. Its death will be spectacular and probably brief. The competition for largest star is, well, messier than it sounds. WOHG64 in the Large Magellanic Cloud, about 160,000 light-years away, recently dimmed dramatically due to a dust-shrouded mass ejection and may now rival or even exceed Scuti in radius. But the distance makes precise measurement genuinely difficult. Both stars are approaching what's called the Hayashi limit, the theoretical maximum radius on the HR diagram, beyond which a star's own convection processes force it to contract. The universe has a size limit for stars, and we're watching the biggest ones bump against it. Which of these stellar behemoths would you most want a front-row seat to watch go supernova from a safe distance, obviously? Drop your answer in the poll below. And if you've got a wild fact about stellar physics or extreme stars that belongs on this channel, put it in the comments. Your fact might become a future video. The Sun is not small. By every human reference point we have, it is incomprehensibly large. But in a galaxy of 200 to 400 billion stars, it is definitively average. And the stars that sit at the far end of the size spectrum, Betelgeuse, Scuti, WOHG64, are so large that they blur the line between star and region of space that happens to be on fire. There are almost certainly larger stars we haven't found yet, hidden behind dust clouds or simply too far away for current instruments to resolve clearly. The Milky Way alone may contain undiscovered hypergiant types we don't have a category for yet. The universe is under no obligation to stay within the limits of what we've already catalogued. Explore the rest of the channel. There is a lot more where this came from.